Okay, you're right. I'm just going to put a YouTube clip on of the work we did today in class, which was Pythagoras' theorem. It's quite easy. And this is how we're going to be running online lessons now. So make sure you have a look at this if you weren't in class today. Make sure you understand the work. Remember, you need to contact me if you can't. And we'll see how we go with this. So Pythagoras' theorem, even though it's been given the name or it's been ascribed to Pythagoras, lots of other people were using it well before Pythagoras came along. But Pythagoras proved it. So I know other people used it, but Pythagoras did a proof. And it was pretty cool. The Babylonians, the Egyptians, the Chinese, all these people were using the relationship and probably may have had proofs with it. But Pythagoras is the one that has retained or been retained, and the one that we ascribe the theory to him or his brotherhood. And it was not just a brotherhood, but a sisterhood. And he was a philosopher, a mathematician. He had views on how to live life, what to eat, all sorts of things. And it was pretty progressive for his time. But anyway, let's have a look at his theorem in regard to geometry of the right angled triangle. So what we have here we have a right angled triangle. And Pythagoras said that if you create a square on the long side of a right angled triangle and squares on the short sides of those right angled triangles, well, the square of the long side equals the sum of the square of the two other sides. And now there's a nice proof of that on hot maths. So, no, hold on. If you go to the hot maths site and demonstrating Pythagoras' theorem, so here we go. There's a triangle. We create squares on either side. And we take the big square off the long side. We take the short square. We cut it in a certain way and move it over. And then take the smaller square and whack it in the middle. Now, that's just a physical proof. Pythagoras actually used an algebraic proof, which was really cool. And his algebraic proof is a little bit beyond what we're going to do, because the algebraic proof requires a level of algebra that is beyond, and it requires this little bit here, which is a bit of algebra that we haven't done yet. But have a look at that image and then go back and go, look at that image. And you can see what we're talking about. Okay, so it doesn't matter what right angled triangle you've got. The square on the long side equals the square on the short sides added together. The squares on the short sides added together. Now, the first thing we need to know is, well, what's the long side? Well, the long side of any right angled triangle, we call it the hypotenuse. And it's always, always, always opposite the right angle. Now remember that the right angle, which is indicated with a little square, means it's 90 degrees. And I'm just going to shut the door. So this long side over here, we just want to call it the long side, which will give it a name. And we call the name hypotenuse. And it's a funny name because I think it's Greek, but it doesn't come from the English language, and it comes from an ancient language. I think it comes from the Greek, hypotenuse. There are names for these other two sides, but we're just going to call them the short sides. because it doesn't matter which way you add them, because it doesn't matter which way you add two things. But you've got to get the hypotenuse correct. So let's have a look at these questions over here, exercise 3K. In a right-angled triangle, the is the longest side. Oh, well, that's hypotenuse. We just said that. Oops. Try and write that a bit neater. The hypotenuse is the longest side in a right-angled triangle. Okay, now what I want you to do is I want you to look at question 4 and see which letter marks the hypotenuse. You should be able to see it rather quickly because remember I said it was opposite the 90 degrees, which is opposite the little square located in the triangle that says that it's a 90-degree triangle. So hopefully in the first one you went, that side's opposite, so C is the hypotenuse. Have a look at B. That side's opposite, so X is the hypotenuse. And the last one, have a look at it, get an answer in your head. That side's opposite, so U is the hypotenuse. Okay, so what else what else do we need to do? Well, we can decide whether or not a triangle has a right angle if those things hold true. If the square on the hypotenuse equals the square on the other two short sides, well then you must have a right-angled triangle, which is really good because right angle means a 90 degrees, which means it's perpendicular, so your lines are straight. And lots of builders and field markers use right-angled triads to make sure that they're at 90 degrees, so you get straight lines. And we call these triads Pythagorean triads. So what we need to do is to have our calculator ready to go because we're going to need to do some things. Well, how do I work out the squares? Well, squaring's pretty easy. To work out the area of a square, if this length was, I don't know, let's use a different colour. If this length was 8, well, the area of the square is 8 times 8. And we should know that 8 times 8 is just 8 squared. We can type it like that on a calculator. Well, if this side was B, the area of that is B times B. And that is B squared. So we need to become good at that. So if we're looking at 3 numbers to find out if they're a Pythagorean triad, all we need to do is go, does the longest one squared equal the sum of the other 2 squared? Does 6 squared, so we're looking at this one, does 6 squared equal 3 squared plus 4 squared? Well, 6 squared is 6 times 6 is 36. Let's just double check that on our calculator. I'm just going to change the setup. So 6 squared, you have a little square button. Oh, that's 36. Beautiful. 3 squared is 9 and 4 squared is 16, and you add them together and you get 25. Let's just double check that. 3 squared plus 4 squared, 25. Fantastic. Oh, but that doesn't work. That doesn't equal 36, does not equal 25. So 3, 4, 6 does not make a Pythagorean triangle, and it means if you drew that 3, 4, 6 triangle, it wouldn't have 90 degrees. Okay. Let's try this one, 3, 4, 5. Well, that's pretty cool because we've already got some of those numbers. 5 squared, does it equal 3 squared plus 4 squared? Well, we already know that 3 squared plus 4 squared is 25. We go to our calculator. 5 squared, oh, it's 25. Hey, that works. That is a Pythagorean triad. 3, 4, 5 makes a right angle triangle. Beauty. Now, there's a really cool thing on your calculator. So I'm going to try another one. I'm going to try 9, 12, 15. And I want you to watch this. So 9, 12, 15. Remember those numbers. You can do this all in one go on your calculator. 9 squared. Now you have to use this special button. You have to hit the alpha button, the purple button up the top here, and hit this one that's got X and some side I can't see. It's got the 2 purple dots, and you get those 2 dots. And you're asking 9 squared equals, we'll go 12 squared plus 15 squared. And what it'll do, it'll give us both answers and we can compare. So I'll just press equals. 9 squared is 81, press equals again. Oh, 12 squared plus 15 squared. Oh, Mr. Tonkin, you did it the wrong way around. You meant to do 9 squared plus 12 squared. Okay, so let's do it. 9 squared plus 12 squared. Oh, come on. 12 squared. Does that equal 15 squared? Press equals. 9 squared plus 12 squared, 225. 15 squared, 225. Oh, they're equal. And I can write it out if I want, because I just 9 squared plus 12 squared. Does that equal 15 squared? Well, 9 squared plus 12 squared is 225. And 15 squared is 225. So yes, that does make the Pythagorean triad. Okay, so what do we do? What can we do? What we want to do is we want to prove a right angle triangle. Well, we actually just proved this one, but I'm going to do it in a better way and more, because when we write a proof, we've got to be very particular. So here's 11a. Does 15 squared equal 9 squared plus 12 squared? We already know it does, but let's go through the proper proof. If I take the left-hand side, well, that's 15 squared, and that equals 225. We've already said that. Then we take the right-hand side, and that's 9 squared plus 12 squared. And we also know that equals 225. So therefore, the left-hand side equals the right-hand side. So it's a right angled triangle. Now there's some things in here you need to know. 3 dots written like that is shorthand for therefore. RHS stands for right hand side. And LHS stands for left hand side, which is all appropriate in a mathematical proof. Let's try another one. Let's try 5, 6, 8. Let's try this one here. 5, 6, 8. So this is 11a. What's the longest side? Oh, 8. 8 squared. Does that equal 6 squared plus 5 squared? Well, we take the left-hand side, equals 8 squared. And I'd use my calculator, make a 8 squared, press equals 64. And then I take my short sides, the right-hand side. Does 6 squared plus 5 squared equal? Well, 6 squared plus 5 squared. And I can do it all in one go on my calculator. 6 squared plus 5 squared. 61. Oh, not quite. So the left-hand side does not equal the right-hand side. So therefore, not a right-angled triangle. So that is an introduction to Pythagoras. Okay? Pythagoras said, and other people knew it as well, that the square, and you should write that, the square on the hypotenuse of the hypotenuse in a right-angled triangle is equal to the sum of the squares of the other two sides. Now, you don't want to be writing that all the time, so we can write it with a mathematical formula. So you draw yourself a nice little right angle triangle. That's a bit wonky, I'm sorry. And we'll call this C, and we'll call this A, and we'll call this B. And we can just write C squared, because that's a hypotenuse, equals A squared plus B squared. And that's much quicker and much easier to write than that big statement. The square of the hypotenuse in a right angled triangle is equal to the sum of the squares on the other two sides. A nice neat diagram and a mathematical equation states that. As long as you can find the hypotenuse, you can use Pythagoras. So you need to finish the questions that were set for this, and make sure, so the questions that we were doing for this exercise are here. Exercise 3K, 3, 4, 5, 7, 3, 4, 5, 7. So I did a couple of 5, we wrote 3, we did 4, and I did 1 of 7. You need to go and have another go with some of those.